Good morning, students. Welcome to Finite Element Methods class. I am B. Rakesh, Assistant Professor in Mechanical Engineering Department. In this lecture, I am going to discuss one important topic in application heat transfer. The topic is heat transfer analysis for fins. In order to increase the rate of heat dissipation by convection from a given primary surface, additional surface may be added. The additional material added is referred to either as extended surface or fin. A familiar example is in motorcycles, in which fins extended from the outer surface of the engine to dissipate more heat by convection. A schematic diagram of such a pin array is shown in figure. This is a good example of a heat sink. L is length of the pin, W is width of the pin, T is thickness of the fin. We shall assume that there is no variation in temperature in thickness and width, width of pins, and the temperature varies only in the length direction of the fin. The fin analysis is a common example of one-dimensional heat transfer problem. One end of the fin is connected to a heat source whose temperature whose temperature is known, and the heat will be transferred to the surrounding through the perimeter surface and end. Usually fins are made up of two types, that is straight fins, second one tapered fins. Let us discussing about straight fin analysis. Consider a straight fin whose area of cross section is uniform throughout its length as shown figure. The figure shows heat transfer in straight rectangular fin. Let T1 and T2 are the temperatures at node 1 and node 2. L is the length of fin, W is the width of the fin, T is the thickness of fin. H is heat convection coefficient, T ambient is surroundings temperature. In fins, the heat is transferred from the heat source to the surroundings by conduction along the length and convection through perimeter surface, that is lateral surface. And also convection through end surface. We can formulate the thermal stiffness matrix containing the above discussed condition, that is conduction and convection parts. Assume the fin as single element having two nodes 1 and 2. The thermal stiffness matrix for pure conduction is given by. In previous class we derived thermal stiffness matrix for pure conduction, that is K equal Ka by L 1 minus 1 minus 1. K means thermal conductivity of the material, A is the cross sectional area, and L is length of the material, length of the pin. Second condition is the thermal stiffness matrix for convection through the perimeter surface is given by K HP equal HP L by 6 2112. This is also derived in previous class. This is derived from the convection part of stiffness matrix, that is K equal to integration S H n transpose into n ds. The surface is intervals from 0 to L, H n transpose n. ds means ds equal to P into dx. P means perimeter of the fin and dx is n is shape function for one dimensional bar element, that is n1 equal to 1 minus x by L, n2 equal to x by L. Now substitute n1 n2 in this equation, we get HPL by 6 2112. The thermal stiffness matrix for convection through end surface is given by K HE equal to HA0001. This is also derived in previous class. The overall thermal stiffness matrix can be obtained by combining all the three matrices, that is 1, 2, 3 matrices, that is K equal to KK plus KHP plus KHE. KHE. K equal to Ka by L 1 minus 1 minus 1 1 plus HPL by 6 2 1 1 2 plus HA into 0 0 0 1. This is equation number 4. Now calculate thermal force vector for the fin subject to perimeter and end convection is given by F equal HPL T infinity plus QAL by 2 into 1 1 plus HA T infinity 0 1. This is also derived in previous class. This equation we obtained from thermal force due to lateral surface heat convection is given by integration S H T ambient H T ambient into N transpose ds. N transpose ds. ds equal to pdx. Now substitute shape conditions, shape functions n1 n2, that is n1 equal to 1 minus x by L, n2 equal to x by L. We get h PL T infinity by 2 into 1 1. Thermal force due to internal heat generation is given by integration V N transpose QA QdV, dV equal to A dx. Now also substitute shape functions n1 n2. We get QAL by 2. The total force is the total force, that means thermal forces due to lateral surface heat convection and internal heat generation, that is HPL T infinity plus QAL by 2 into 1 1. The finite element equation for fin element is given by K into T equal F. F is thermal force vector. Now substitute above equations in this this finite element equation, that is Ka by L 1 minus 1 minus 1 1 plus HPL by 6 2 1 1 2 plus HA 0 0 0 1 into T1 T2 equal to HPL T infinity plus QAL by 2 into 1 1 plus HA T infinity 0 1. Now multiply with Ka by L in this matrix. Now multiply those terms and uh, add those matrices, that is Ka by L plus HBL by 3, Ka by L plus HPL by 6 into 2, that means HPL by 3 minus Ka by L plus HPL by 6 minus Ka by L plus HPL by 6, Ka by L plus HPL by 3 plus Ha into T1 T2. Similar to right side, HPL T infinity plus QAL by 2 into 1 plus HA T infinity into 0. Second term, HPL T infinity plus QAL by 2 into 1 plus HA T infinity. This is equation number 7. Since the quantity of transferred heat through the end surface of fin is negligibly small compared to that through perimeter surface, we can omit the corresponding convection part. Also, if there is no internal heat generation, the term QAL can be removed. Now simplify above seventh equation. We can get Ka by L 1 minus 1 minus 1 1 plus HPL by 6 2 1 1 2 T1 T2 equal HPL by T infinity by 2 1 1. This is also negligible. This term also negligible. Finally, we get HPL by T infinity by 2 into 1 1. Now similar to multiply and add similar positions, that is Ka by L plus HPL by 3 minus Ka by L plus HPL by 6 minus Ka by L plus HPL by 6 Ka by L plus HPL by 3 into T1 T2 equal HPL T infinity by 2 into 1. Next HPL T infinity by 2. This ninth equation. Next one is heat transfer through tapered fin. For the fin made of tapered cross section as shown in figure, the thermal stiffness matrix due to conduction and convection are given. This is the L is length of the tapered fin length. The conduction part of the element, the conduction part of the thermal stiffness matrix is given by Kk equal Ka by L into 1 minus 1 minus 1 1, where A is the average area of the cross section. That means A equals A1 plus A2 by 2. A1 is area at node 1, A2 is area at node 2. The part of the thermal stiffness matrix is due to convection through perimeter surface given by KHP equal HL by 12 3P1 plus P2 P1 plus P2 P1 plus P2 P1 plus 3P2. This is equation number 2, where P1 and P2 are the perimeters at nodes 1 and 2. The thermal force vector is given by F equals H T infinity L by 6 2 P1 plus P2 P1 plus 2 P2. This is equation number 3. Now write finite element equation for tapered fin is given by KT equal F. K is thermal stiffness matrix for tapered fin, that is Ka by L 1 minus 1 minus 1 1 plus HL by 12 3P1 plus P2 P1 plus P2 P1 plus P2 P1 plus 3P2 into T1 T2 equal H T infinity L by 6 into 2P1 plus P2 plus 2P1 plus P2, P1 plus 2P2. This is the thermal force vector. This is the equation for, this is the finite element equation for heat transfer through tapered fin. Let us discuss one problem on heat transfer through fin analysis. The problem is, find the temperature distribution in a straight fin with the physical properties as shown in figure, that is thermal conductivity K equals 70 watt per centimeter degree centigrade, convection heat transfer coefficient H equals 10 watt per centimeter degree centigrade, H equals 10 watt per centimeter square degree centigrade, temperature at the root of the fin to T naught equal 140 degrees centigrade, surrounding temperature, that is T infinity equal 40 degrees centigrade. Assume that the free end of the fin is insulated. Consider two elements. This is the given figure. Now divide this figure into two parts, that is element 1 and element 2 temperatures, and also give the nodes 1, 2, 3 and temperatures T1, T2, T3. L1 equal to L by 2, that means 2.5 centimeters, L2 equal 2.5 centimeters. K1 is thermal conductivity for element 1, K2 is thermal conductivity for element 2. Both are equal, that is K1 equal K2 equal to K, and also A1 equal to A2, L1 equal to L2 and H1 equal to H2. The given data is K1 equal K2 equals 70 watt per centimeter degree centigrade, L1 equal to L2 equal 2.5 centimeters, H1 equal to H2 equal 5 watt per centimeter square degree centigrade. Area A1 equal to A2 equal A equal pi by 4 d square. The diameter of the fin is 2 centimeters, that is 2 square. 4 get cancelled, that answer is area equal pi centimeter square. In both elements, heat is transferred through body conduction along the length and convection through the perimeter surface, that is lateral surface, and convection through free end surface, since the free end is insulated. For such condition, the finite element equation for these two elements are given as follow. For element 1, the finite element equation given by Kt equal to F, that is K1 A1 by L1 1 minus 1 minus 1 1 plus H1 P1 L1 by 6 2 1 1 2 into T1 T2 equal H1 P1 L1 T infinity by 2 1 1. Now simplify this equation. That means now multiply these outside terms with inside terms, that is K1 A1 by L1 minus K1 A1 by L1 minus K1 A1 by L1 minus K1 A1 by L1 plus 2 H1 P1 L1 by 6 H1 P1 L1 by 6 H1 P1 L1 by 6 2 H1 P1 L1 by 6 into T1 T2 equal H1 P1 L1 T infinity by 2 into 1 H1 P1 L1 T infinity by 2 is equation 1. Similar to for element 2, now uh, replace the terms 1 with 2, that is K2 A2 L2 minus K2 A2 by L2 minus K2 A2 by L2 K2 A2 by L2 plus 2H2 P2L2 by 6 H2 P2L2 by 6 H2 P2L2 by 6 2H2 P2L2 by 6. The temperature uh, for element 2 temperature nodes are 2 and 3. So take T2 T3 equal H2 P2 L2 by T infinity by 2 H2 P2 L2 T infinity by 2. We know that K1 equal K2. So take K, A1 equal A2 equal A, L1 equal L2 equal L, H1 equal H2 equal H, P1 equal P2 equal P. Now substitute these terms in above equations and also write global finite element equation for the whole fin is given by Ka by L minus Ka by L 0 minus Ka by L 2 Ka by L minus Ka by L 0 minus Ka by L Ka by L. These two elements having three nodes. So global finite element equation having size 3 by 3 plus 2 HPL by 6 HPL by 6 0 HPL by 6 4 HPL by 6 HPL by 6 0 HPL by 6 2 HPL by 6 into 3 nodes, that is T1 T2 T3 temperatures equal to 3 thermal force vectors, that is HPL T infinity by 2 HPL T infinity HPL T infinity by 2. For equation 1 H1 P1 L1 T infinity by 2 at node 2, this is 1 1 2 1 1 H1 P1 L1 T infinity by 2 1 2 H1 P1 L1 T infinity by 2 same 1 2 3 1 1 1 2 is HPL T infinity by infinity 1 1 2 3. In equation 1 having 1 2 term, in equation 3 having also 1 2 term. Addition of this two term that equal to H2 HPL T infinity. Next similar to the odd one HPL T infinity by 2. Now calculate all those terms, that is Ka by L, that equal to 70 into A is area pi by L 2.5, that equal to 88 watt per centimeter, and also calculate HPL by 6. H is heat transfer coefficient 5 into perimeter. The formula for perimeter equal to P equal to pi d 5 into diameter 2 centimeter, that is 2 pi centimeters 5 into 2 pi into length 2.5 by 6, that is 13 watt per centimeters. HPL T infinity by 2 H equal 5 into P 2 pi into L 2.5 into T infinity 40 degrees by 2, that is 1571 watts. Now substitute these values in equation 3. We get 88 minus 88 0 minus 88 176 minus 88 0 minus 88 88 26 13 0 13 52 13 0 13 26 into T1, that is 140 degrees. T2 T3 equal thermal force vectors F1 1571 F2 3142 F3 1571. Now simplify this equation. Minus 75 into 140 plus 228 into T2 minus 75 into T3 equals 3142. This is equation 1. Next 0 into 140 minus 75 into T2 plus 114 into T3 equals 1571. This is equation 2. Now evaluate these two equations by using calci. We get T3 equals 67.7 degrees centigrade, T2 equals 82.1 degrees centigrade. Temperature at node 2 is 82.1 degrees centigrade. Temperature at node 3, that is T3 equals 67.7 degrees centigrade. I hope this is very clear to everyone. In the next lecture, I will going to discuss few problems on heat transfer analysis of pins. Thank you for watching. Please do like and subscribe my channel for more updates.